Okay, aqueous chemistry is a standard that's really a lot about equilibrium and how different species interact in solutions. And the first thing is to do with solubility. Now, solubility is to do with how much of generally a salt, such as magnesium hydroxide in this example, is going to dissolve in 1 litre. So if we have 1 litre of solution over here, or water, how much of this, when we put it in there, will actually dissolve. Now, the salts we're dealing with are not the ones that are completely soluble. They're ones that are sparingly soluble. That's what we're kind of interested in. And if we're to write an equation, now in chemistry we're kind of talking about a chemical equation. Don't think about it as being a maths equation, it's a chemical one. So I'll do the equilibrium kind of sign there, and that's going to split up into magnesium ions and 2 hydroxide ions, and we should put AQ here, which I'll try and do with this pen. And we've got, now initially when we start putting magnesium hydroxide in it, it'll completely dissolve and it won't be at equilibrium. There'll be no solid starting to form or anything like that. And we'll keep on adding it, and eventually we'll get to a stage where it becomes saturated. Now saturated means we cannot add any more without it just forming more and more solid on the bottom or around in the solution. So if we keep on adding past this point, it doesn't change anything, it is at equilibrium. And what's happening here is going back and forth all the time between the solid and the ions in solution. We've got that forward and reverse reaction going all the time. Now the actual solubility expression, or the definition of solubility I should say, relates to how much of this solid here will dissolve in solution. So it's how much of that solid will dissolve. Okay? So if we have say for instance 0.15 moles of this will dissolve, that is the solubility, and we call it S. Now because of the relationship on the other side of the equation, that means that the concentration of the magnesium ions is going to be 0.15, and that's moles per litre. Now solubility also has a concentration, and that's moles per litre as well. Now the hydroxide ion concentration, because there's a 2 there, will be double that, and that'll be 0.3 moles per litre. Okay, so that's how the concentration of these species here is related to S. Okay. Now when it comes to writing Ks, which is just the equilibrium constant for this particular equation, it's just going to be magnesium with the square brackets, and then it's a multiplication, OH minus the hydroxide ions, and they're squared because of the 2. Now because this is a solid, it's not shown in there. In fact, in all these solubility expressions that you're going to do, Ks values, you don't ever have over anything. The solid is a constant, so it doesn't appear in this equation. Okay? So for instance, if you had AgCl as a solid, if you're asked to do the equation, it's a chemical equation, don't confuse them. It would just be Ag plus and Cl minus, and you again should show the state, which is aqueous. If you want to do the Ks, it's just going to be this time Ag plus and Cl minus. I should put the state in there as well, but I can't fit it very easily. Okay, so know the difference between the actual equation and know the expression, and also, for instance, in this case, if we're dissolving silver chloride into a solution, and say in this case we had something like, we'll give a more likely number, say 2.0 times 10 to the -5 was the S value, that's a solubility, and that's in moles per litre. that would mean the concentration of the silver ions would be 2.0 times 10 to the negative 5, and the chloride ions would also, because it's a 1-to-1 relationship, 2 times 10 to the negative 5 moles per litre as well. Okay, so that concept of saturated is an important one as well. That means, I'm just repeating this, that when you dissolve a solid like silver chloride in solution, when it's saturated and you can't dissolve anymore, that means it is at equilibrium. Okay? Now, just one or two extra points. We're talking about salts. Some students struggle to know how to separate these salts out, because a salt consists of positive and negative species coming together to form this ionic solid. Now, when we look at something like sodium chloride that we're familiar with, we know that when you put it into water, it's going to separate into sodium and chloride ions. And something like this, which we may not be familiar with, you should recognize, for instance, that the silver is going to be Ag+, and through, even though you don't know the charge, you know that probably came from over there in terms of drop and swap, and that would be the chromate ion. Okay, and some of these are a little bit more familiar. I mean, the Pb, you might think, well, I'm not sure what charge that is, but again, there's a 2 down here, so from drop and swap it's there, and you should know the hydroxide ion is the other species it's going to form. Just the same as here, the 3 came from over there. So it's just that ability to separate salts out into the cations and the anions. Now, just one other last point that I didn't mention earlier on. Say we had lead hydroxide in equilibrium. This equilibrium, just like equilibriums from year 12, is dependent on temperature, so often it'll be at a certain temperature, and as you increase the temperature, more can dissolve, which means if more can dissolve, equilibrium of course is going in that direction. Okay, so anyway, just another minor point.